Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So this is completely unrelated to the talk I was giving yesterday about transactional memory. In that this is some of the more recent research work that I've been involved in collaboration with Rebecca here and Ross McIlroy and Martina Bardi, who I was working with on this at Microsoft. And this is really looking at some of the questions that we faced when writing software to run on the Barrelfish Research OS, where we were finding, as I'll illustrate with some examples in a moment, that the basic programming model for sending messages between processes was extremely complicated. I'll show what that looks like for a simple program that's just sending a ping-pong request between a pair of processes. And I think that will quickly get home the fact that this was a very much a programming model that was designed for efficiency and portability between different hardware platforms, but not really designed for direct use by programmers. More recently, we've gone on to look at using this same programming model on a traditional OS, both on Linux and on Windows, and to use it for writing software that's doing a lot of I/O operations. So instead of sending and receiving messages as we were doing in Barrelfish, we're using these same abstractions for handling asynchronous I/O to the disk and to the network. So in this talk, I'll have a range of examples, some of them coming from Windows to try and have a fairly familiar feel to them, and some of them coming from Barrelfish to illustrate the original setting that we were doing this work in. Now, this talk comes from a paper we had at UPSLA last year. So it's about 6 months ago that we presented that. And the work we're talking about, at least for Barrelfish, has now been checked into the public source tree. So if you have a look at the Barrelfish website, all of this is in there with slightly more cumbersome syntax, but broadly the same ideas. And I can give you some pointers to that later on if you're interested in taking a look at it. So let's start out with a simple example of normal synchronous I/O on an OS like Windows. It would look largely the same if this was written on Linux, so it's common across most OS. And what this example is doing is it's a function that's going to process a file. It takes, in this case, a file handle that identifies an already open file that it's going to get the data from. And it's a bit of a synthetic example. It's going to do a lot of processing, read in all of the data from the file, and compute a single integer output value that it'll store to the location that output points to. And so what the loop is doing here is reading in buffers of data from the file, 1K at a time. We start out by allocating enough memory to hold all of the contents in RAM at the same time. So again, it's a little synthetic. You wouldn't necessarily want to do this. And then at the end, we do some processing to compute the output value, and we deallocate the buffer at the end. And this is a relatively simple way of writing the example, but it's going to perform very poorly on most implementations. So one reason for that is it's only exposing read operations to the file system one operation at a time. So there's no opportunity for software for the disk device to pipeline a series of disk accesses. It's going to be doing a synchronous request for a 1K block, returning that to the application, doing a synchronous request to the next K block, and returning that. So getting good performance here is very dependent on the rest of the software, identifying the access pattern, and doing appropriate prefetching of these accesses. And then we've got a problem if we want to handle multiple files. Let's imagine we've got two independent files and want to process both of those. Either we're going to have to process them serially, and that's going to be probably leading to poor performance if we're doing all the I/O for one file and then all the computation on that before starting the I/O for the second file. We might want to keep the disk busy fetching the data from both files and overlapping some of the computation with that I/O. The alternative we could do for processing multiple files is to introduce threading. So have one thread processing the first file and a second thread processing a second file. And so that would be a reasonable thing to do, but it introduces all the complexity that comes from writing a multi-threaded program. We need to sort out how to synchronize the threads, how to avoid any data races on shared state that they might be accessing. So it's a shame to introduce threading into an example like this that is probably an I/O-bound process rather than one that's bottlenecked on the CPU. So operating systems, including Windows and including Linux, have introduced abstractions for performing asynchronous I/O. And this tries to get around the limitations of that synchronous interface in terms of performance by letting the software expose a large number of I/O requests to the file system at the same time, potentially letting the device drive issue multiple requests to the disk, getting better performance that way. And the downside of that, though, is that the programming abstractions for asynchronous I/O in a traditional OS are extremely complicated. So this is that same example that's just reading a series of blocks from a file, doing some computation, and returning an integer result. And you can see there's all this other stuff going on around the outside of the basic reading and computation. And this is still with a lot of error handling code removed to make it fit on a single slide. So what's going on here is we start out by creating this I/O completion port abstraction, which is something that Windows provides for synchronizing with the I/O. The asynchronous requests are linked with a completion port, and then an operation on the completion port lets the software query when a file I/O has completed by the disk. We've then got the main loop tucked in here that's actually dealing with issuing the requests. So this getQueuedCompletionStatus function is the one that's looking at seeing if there's been a completion of an asynchronous request we issued. And if there has, it does some bit of computation and issues a new request to keep the device busy. At the end, we have to wait for all of the requests we've put in flight to finish. So we've got this cleaning up loop here. And we've got some temporary data structures, this buffer that we had to allocate at the end. And as I mentioned, this is even with lots of error handling code omitted to keep the example short. And although we'll get good performance with this, we've still got some of the problems with that synchronous process file operation, in that the operation is not composable, in the sense that if we want to process two files, we can't do that and still get the benefits of asynchronous I/O and still let those two processing operations go on concurrently with one another. We'd either have to serialize them again or put them into different threads. We can't say that we want to start processing two files asynchronously and still have this same programming model. Let me backtrack a bit and give another example just to motivate this work, and just to make the Barrelfish setting a little more concrete by showing what a simple message passing example would be like in this setting. And this is going to be about the simplest example I could come up with. We're going to have two processes. The first one is going to send a message to the second and then get a response back from it. Now, as Rebecca might have mentioned, we have an interface definition language that describes the kinds of messages that are carried on a channel. And the definition in this case is saying that we've got a ping operation, that it's an RPC, which means it's got kinds of messages that go in both directions, a request and then a response, and that the outgoing message carries a 32-bit integer parameter, and the response carries a 32-bit integer result. Now, for the basic asynchronous message passing abstraction that we have a stub compiler that takes the interface definition language and creates a set of C function definitions that can be used on the different hardware platforms that we support. So we get these stubs for different platforms, the Intel SCC multi-core chip, communication over shared memory between the two processors on a conventional Intel or AMD 64-bit or 32-bit chip, then experimental systems like the Beehive processor running on an FPGA. So this abstraction gives us portability across all of these different multi-core platforms that we support. But it really doesn't give a very straightforward to use programming model. And a lot of the consequences of that come from wanting to have that portability and to get good performance, irrespective of whether we're running on a system where messages are passed through shared memory or whether they're passed through some kind of hardware support like the Beehive or the SCC processor gives us. So here's what the portable C interface looks like for the underlying asynchronous messaging. So just for that RPC ping-pong operation, the first function here is sending a ping message on a message channel. And I'll ignore the details about how we actually set up the message channel to start with. But the basic idea is that this binding object refers to a message channel that we've already opened. So calling send ping is going to send a ping message with this value here as the parameter in it. And now the difficulty is that this send operation can fail. So we either get back an OK status code if the message has been sent, but the send might fail because perhaps we're running on a hardware-supported messaging system and the hardware's buffers are full, and so there's nowhere to put this message. So if the send fails, we need to use this second function to register a notification for when it's worth trying the send a second time. So we call the register send function, we say which channel we're interested in, and we provide a function callback here, which is just a pointer to a C function that's going to be run when the message channel has new space in it. Now, to get the response, we also have to deal with callbacks, and we do that with this register receive ping response function. And that lets us, again, specify a C function to execute when the ping message comes back to our process. And then the final piece of work here is the event dispatch function, and that says that we should block waiting until one of these callbacks executes. So let me show you how this interface would be used to actually write the main part of this ping-pong function. We start out by registering a handler that's going to execute when we get our response. We then have a loop that's going to try to send the message and see if we manage to succeed or not. Now, if we fail because the message channel is busy, then we allocate a temporary buffer to keep track of the information that we're wanting to send. Here it's just a constant 10 value. And we register a callback for when it's worth trying to send a second time. And then otherwise we check that everything's OK, and we go into this event dispatch loop, waiting for us to get a response back from the process that we're interacting with. We've got to write the two message handlers as well. The response handler that runs when we get the response in is going to just print the value out and then exit the loop. And the resend handler, which is going to execute if we found the message channel was busy and need to try a second time, is going to try sending, and then it's got to deal with the case where the message channel might still be busy, and we've got to try a third time. So there's lots of stuff to write, even for this simple message send and receive operation. We've got some dynamic allocation going on here. There's lots of different functions that can succeed or fail in different ways. And so when we're building an OS structured around message passing, it's clearly very difficult if even sending and receiving a single message ends up taking a slide full of code. And you might reasonably ask, why did we build this rod to beat ourselves with, rather than just having a simpler message send and receive operation? And there were a few reasons here. One is that often we'd like to be able to get better performance by having a process do some work while it's waiting for a message response to come back in. So instead of spinning, waiting for the message, we go and do some computation and then pick up the messages once they arrive. We'd like to make it easier to write, or possible to write, a server that deals with multiple client processes. And so we don't want the server to get stuck, blocked, waiting for a message from one of its processes. We want it to be able to respond to messages from different processes. And we didn't want to introduce threading in this kind of setting, because we're using messages at a very low level in the system, and we might not have a thread scheduler there, for example. So we were generally motivated by these two performance criteria, and then this goal to keep a very lightweight runtime system that can operate below the level at which we might have threads or garbage collection, and which would be portable for use on the diverse hardware platforms that we've been working on in Barrelfish. So the work that we've done here is a system called AsyncronouS that aims to provide a middle ground between these two forms of I/O. The synchronous I/O that's straightforward to use but gives poor performance or poor ability to support multiple remote clients, and asynchronous I/O that's difficult to use but has the potential to give good performance. And we aim to be somewhere in the middle, trying to provide a programming model that's largely similar to writing synchronous I/O operations, but that's able to be implemented in a way that gives us performance that's comparable to an asynchronous interface. So the focus here, just comparing this a little with a lot of the related work that's been done in this area, is we're really looking at performance and the ability to use messaging in low-level settings such as the system processes in Barrelfish. And that's guided a lot of the design choices to try to ensure we can keep a lightweight implementation. We've developed just a small number of constructs that we've added to C. There's a construct, as I'll show in a moment, for starting work that's going to run asynchronously with the main line of the thread. There's a mechanism to synchronize with asynchronous work, and there's a mechanism to cancel some asynchronous work that we've started, and we don't want to wait to finish any longer. So we might have issued an I/O request and then got to a stage we don't care about the result, maybe because we asked 2 servers and we were happy to take the first response that we got back from either of them. And we also want to build this system so we can add higher level features over it as time goes on. So if you're familiar with some of the other concurrency control work, we've not looked at things like join patterns or futures here. We've just focused on this fairly small set of features for dealing with asynchronous I/O. So let me illustrate this with an example, going back to the Windows case where we had that process file function. And the first thing to see here is that the function is largely the same as the synchronous version that we started with. Some of the differences are we're using these asynchronous C versions of the I/O primitives instead of the normal Windows ones. And we've marked this function as being an AC function, and the read operation we're using as an AC function. We've used this new async block construct in the middle of the function to identify where we're creating work that is able to run asynchronously. So when we say async with some code in it, then that means we should start the code inside running, and then if the code there blocks, then we should go back and execute the code that comes after the asynchronous block. So you should think about this as being a bit different from starting a thread. We're not saying that the code inside the block is actually going to be executing on a separate core and being time sliced on a fine-grained basis with the code after the async block. This is purely describing what happens if we need to wait inside the async. So we'll start executing the read file, and then if that needs to wait getting the data off the disk, then we'll continue back just after the async, go around the loop again, and start fetching the next block at the same time as the first one. And then we have a finish construct around the outside of the function. And that's used for synchronization. It's saying that we should start all the work in the function, but we shouldn't go past this finish point until we've got all of the work completed. So in this case, it will have the effect that we'll go around the loop in the middle, issue the series of I/O requests, and then wait at the finish block until all of the I/O has come back from the disk. We then compute the result and clean up as in the original version of the code. Yeah? So the question is how this relates to doing deferred procedure call. I'm not sure exactly what the semantics of that would be. I think it would differ at a low level in a lot of ways. Here we're just looking at work going on within a single function, and we're executing on the same stack as the process file is called on. And we've got direct access from within the async block here to all of the local variables in the enclosing scope. So I'd be happy to talk a bit later and see what the detailed differences would be beyond that. Yeah. So the question is, what happens when we go into this async block and then maybe get partway through and continue around? When does the actual I/O start happening and the synchronization with the results of that I/O coming back? So what's going to happen here is the the execution continues as normal when we enter the async block. So if you think about the first iteration of the loop, we'll go into the block, I will be 0, we'll call into the read file function, and then internally that's going to use the same completion port mechanisms that I had on the original Windows Asynchronous IO slide. So the call to read file AC is going to issue that IO request, and it's then going to get to the point where it needs to wait for the IO to complete. It will record, I'll show a bit more about the implementation in a moment, but it will record the fact there's one pending IO request on a structure that's linked to the do finish block that we've entered. So the runtime system is keeping track of how many IO requests have been issued for that do finish block. And once it's done that, the runtime system searches back up the stack for the enclosing async and resumes execution afterwards. So each time we go around this loop, we're going to be issuing one IO request. Then at the same time, there's a kind of idle function that runs when there isn't any work otherwise to execute. And on Windows, that idle function will deal with updating these counts of IO operations that have completed. So as the read operations are completed by the file system, that's going to update the Windows completion port to signal that the IOs are complete. And this kind of scheduling loop we have in the AC runtime system is going to update the statistics on this do finish. So that will decrement the counter, and once the counter's down to 0 again, that will enable execution of this code after the finish. I'll come back to a bit more about the implementation later on and can clarify that further if that's useful. Yeah?
So in this particular loop, you test the OK flag, but now, the first time through, you don't actually update OK, and yet you're going to test it when you get back to the second time around the loop. How does that work?
So the main thing to keep in mind is that this is all running on the same thread. So we're not going to need to add any synchronization on these accesses to OK. What's going to happen here is OK will start off as true. We're going to continue around this loop without that flag having any effect. And then there's a convention that I'll come on to in a moment, which is that if an IO request is cancelled because we don't care about its value any longer, then that's exposed by having the read AC function return false. So the convention with all of these AC functions is either they run to completion or they return true, or they are cancelled and tidy themselves up and return false. So what this is doing is meaning that if some code external to this function asks us to be cancelled, then if we've got some reads still in flight, those will return false, and the flag will stop us issuing any further reads to try to get us to finish as quickly as possible. So I've got a few more examples that show cancellation, and hopefully that will help in a moment. Yeah? Which one, sorry? Oh dear, no, I wrote this wrongly. It should be something like the file size divided by the size of the buffers that we're reading. So I think that should be size divided by 1024 in this case. I'm afraid I made a mistake on the slide. Yeah. So what's going to happen here is the read file is going to block internally. The async is going to mean we catch that and keep going around the loop. And then eventually we'll have issued all of the IO requests that we're able to, and we'll wait at the finish. But what can also happen is maybe we've got a function call that's making multiple invocations of this one. So it's processing two files, and it's using async to say that both of these requests can go on at the same time. So although we're blocked inside here at this finish, there might be a bigger async that surrounds our function call and gives us some other work to keep the thread busy with in the meantime. I think I've probably got an example of that in a moment as well. So I'll move on, and then hopefully some of the other slides will cover these topics. So the example here is actually illustrating just that. We want to process two files. We have two file handles, and we want to compute a result based on the two results we get from the two files. And we can do that by making calls into the process file AC function from the previous slide and putting these in asynchronous blocks and using doFinish to synchronize again. So we've got this form of composition in that we're able to use asynchronous IO inside the process file AC function. And we're also able to use that process file AC as a building block in a bigger piece of asynchronous work, processing these two files. So what would happen in practice here is we might get partway through here, we'll get to the first async and call off into the process file AC function. Then that one has issued all of the IO requests for the first file, and so we then wait inside that, and because we're calling it asynchronously, we continue with the code after that asynchronous call. We then go on here and start up the second file, processing that one as well, and then blocking at the finish. And then these two process file calls are going to complete after all of their internal IO and computation is done, and then we'll resume from the finish and return the result here. And exactly what's going to happen is going to depend on the speed of the devices and the speed of the file system internally. Here I was saying that we'll probably be blocking because we wait for perhaps a disk to respond to our IO requests. But if it happened that we were accessing data that was cached in memory, it might be that none of these reads or writes blocks, and we just execute this code straightforwardly at full speed, as I'll show with some performance numbers, with essentially no overhead from the use of the asyncs and doFinishes that weren't used in that latter case. Yeah?
It's like the first one blocks, H1 and H2 doesn't. Does the second OK, is that second statement finish first and then the first one, or do you wait for the first one to complete? Like what I'm wondering about is, like in this case, trivial OK is updated in the same way, but are those two statements executed in the order that they're specified, or in the opposite order?
So we've got there's an operational semantics in the IGÇÖll paper that goes into some of these questions. In this example, what's going to happen is we'll you kind of think about the unblocking within each of these calls as putting a piece of work back on a per thread work queue. So when, let's say that this one finishes first, and we've got all of the blocks back from that second file, we've computed the result. We'll then put on the work queue, we'll put on the work queue the item for the rest of that code after the finish block, and that will include the return to this function and the execution of this operation on OK. And the same thing would happen on the first file. Once all of the inputs have come back, we put on the work queue the computation and this return, including this piece of OK. Now, if both of those bits of code block, then the semantics is non-deterministic. We allow either of these pieces to run, and there's no ordering constraints between them. But we do say that if a piece of code runs without blocking, then it's as if the async and the doFinish were never present. So if this first file, let's say, is in a RAM disk, or all of it hits in a buffer cache, then having the async here doesn't let anything else happen. We can't spontaneously switch from one piece of work to another. We only switch when the thing we're executing is waiting. Okay.
There is a data dependence between the first and second statement. The value of OK flows from the first to second.
So that would happen if it's executed serially, but the semantics we've got here, part of introducing asynchrony is that there'll be some interleaving switching between pieces of code here and here when we block, and that includes being allowed to switch from these pieces of work within the same function.
So with that semantics, it looks a lot like they're just executed in parallel.
So the difference is we're not going to have any fine-grained interleaving between the work. We don't need to have a lock on OK. and we're only going to switch when waiting. So it's more like a kind of cooperative multi-threading rather than genuine parallelism on separate cores. So we tried, both in the semantics and the design of the runtime system, to give this guarantee that the only time when you switch from one thing to another is when you need to wait, rather than having additional interleavings beyond that. Yeah. Of what happening, sorry? So you could certainly write code that performs badly. If you issued a lot of disk requests for 2 separate days. That's
So, right, so in that case, is there any such possibility because of the interleaving? Because if it were a serial transfer, that in that case it would have cached the subsequent request prior. And since the interleaving is possible in this case, the caching may or may not happen, or I don't know how it will take care of it in your case. So, any thoughts on that?
So here we're really just handling getting these I/O requests out to the file system and giving that the opportunity to schedule them as effectively as it wishes to. So we're not going to do anything within the AC runtime system, say to handle the case where we might be doing conflicting operations on different files. If we're creating a file here and deleting the same file here, then the program has made a mistake. They shouldn't be doing those 2 pieces of work asynchronously with one another. So the program would have to either just not put async between those on those pieces of work, or they'd have to add some kind of concurrency control of their own. That's not something we're doing automatically here. So just illustrate another example then. What we're doing here now is providing some extra control over the number of I/O requests that we issue. This isn't the exact syntax that we'd use in practice. In practice, this would be pushed into an I/O library rather than written in every program. But this is just to illustrate the kind of things that can be built over the AC primitives. So what we've got here is a semaphore that is integrated with the AC runtime system. And it's a counting semaphore that we initialize to 100. So we can call a P operation on that semaphore 100 times before it blocks. And then we can use the V operation to raise the semaphore again to unblock one of the blocked P operations. And we can use the counting semaphore in this way to limit the number of I/O requests that we issue. So for example, if the underlying implementation of asynchronous I/O in the OS has some cost associated with each outstanding request, then we might want to reduce the amount of work we're exposing to it so we don't cause some space cost there. And what's going on here is we've got a do-finish loop, so we're going to wait at the end until all of the work we're starting is done. And then inside we're going around a million times, and on each iteration we're claiming one of the values from the semaphore with a P operation on it before starting some asynchronous work. And then once we've done the asynchronous work, we do the V on the semaphore, still inside the async block. So what's going to happen here is we'll start up, go around the loop the first 100 times, and each of those is going to decrement the semaphore, start some asynchronous work, and let's imagine that the work takes a long time and doesn't finish immediately. So we'll go around 100 times doing that, and then we'll block on the 101st time on the P operation. And that is going to be where we'll wait, and the idle thread that I mentioned earlier will be still going and picking up the I/Os as they finish, and it will put the continuation here, the V operation, back onto the work queue each time a piece of I/O completes. So we're going to have this pipelined effect with 100 requests kept in flight at any given time, using the semaphore to synchronize between the I/O requests that are finishing down here and enabling the next iteration of the loop to complete. There's one important thing in this example, and that's that I put the P operation here outside the async rather than inside. And the reason for that is that if I put P inside the async, we'd actually be starting all million requests. We'd be starting the runtime costs of these million async blocks and then blocking inside each of them just after they've begun. Whereas if we put the P outside, that's going to block the outer loop, and we're not going to spin up that million entries. We're just going to have the 100 that we have in flight at any given time. Yeah?
So can you get this sort of pattern to Composable?
Not if it's written as it is on the slide here. And what I'd actually want to do is push this into the I/O library. And so the parameter 100 would hopefully be picked up in some sensible way, either when the process is loaded or there'd be some way of tuning it. And that would apply across all of the I/O operations, or perhaps to all the operations that hit the same particular device at the end. But yeah, that's the disadvantage. I've not thought a great deal about how we'd combine those two effects. So let me say a bit about the next problem, which is how we handle cancellation. And the example here is if we want to add a timeout to an operation. We're wanting to try processing a file using AC, and we're going to then want to let it run for some duration. And then if we've not got the result after that time, give up and return this false status code that I've mentioned before. And we have the final language extension that I mentioned here to handle this, cancel. And cancel should be thought of as saying, well, if there's work that's waiting to finish, then give that a prod and let it try to tell it to finish up quickly. It's a cooperative mechanism in the same way as interrupted exception is in Java. It's not giving us a way to arbitrarily kill a piece of work that might be halfway through. And that's really for the same reasons that there's that cooperative nature to interrupted exception. We don't want to have, we want to be able to give something the chance to restore its own invariant on the state of local variables, the state of other variables that it's manipulating. So what's going to happen here is, let's imagine we execute down through here, and we start both of these async calls. So we'll be starting this first one doing the process file, and the second one doing a sleep for the timeout. And let's imagine that the file finishes first, and we get to the cancel with timeout operation. Now what that means is we look for the do-finish block that has the label with timeout, and then we poke each of the block's operations within this do-finish and tell them to complete their work and then return. So in this case, we're poking this do-finish on the slide, and we look inside, and it's the blocked sleep AC function here, which is going to return with false. We're ignoring the return code in this case. And the second cancellation has no further effect. We've already marked this do-finish as having cancellation requested, and the further cancel is ignored. The semantics of finish are exactly the same as before, though. We're going to wait at finish until everything inside that block is completed. So the cancellation request is not saying we can immediately branch to the finish and continue. It's saying that we try to wake up everyone inside the do finish, have them return false, and then tidy up, and once they've done that, the finish block is eligible to continue past. So let's look at the more interesting case, which is where we had the same example and it went the other way around, where we reached this cancellation here first of all, and we were in the middle of doing the process file. What will happen in this case, we poke the do finish block again, and the cancellation request will propagate into this process file operation that is in flight, because we're looking dynamically at all of the work inside this do finish, not just the work immediately in this one function. And we'll be somewhere inside the inside process file at that point. So we'll have some of these read files in flight, maybe some of them not yet issued. And the cancellation will propagate in and poke the do finish here and all of the blocked work internally inside that. Now, because of the convention I mentioned that work when it's interrupted returns false, that will mean that any read files that are blocked are going to return false. We'll reduce that back into the OK status field, that's going to be false. It'll terminate the loop, so we won't issue any new requests. And then we'll do the cleanup here and return false from the process file function. And then back out of here, you notice that the process files result forms the overall result of this function. So what that means is if we do get the cancellation request from the timeout before we have issued all of the IOs, then we'll cancel them and we'll definitely be returning false from process file. But if we have a data race between, or a kind of race between the cancellation request here and a device driver finishing some of those IOs for us, then it'll come down to which of the functions in process file, which of the reads in process file manages to return successfully. So if all of these manage to return successfully before the cancellation reached us, then we return OK as true, and that forms the result of the function here. But if anything was cancelled, then we return false. So this is a convention we developed called exact cancellation. And this is purely a convention. It's something we follow in the built-in primitives for AC, and we've used in examples like that one. But there's no kind of static checking or mechanism to enforce it at the moment. And what exact cancellation means, as I mentioned, is if we're in an AC function, then either it returns true and completes successfully without cancellation, or it returns false and tidies up any half-done effects that it's had before returning. So, of course, this is perhaps easier said than done, and there's lots of different cases for different I/O requests. Read is the obvious, straightforward case, but a write would be more tricky. We have to decide what to do there. But we give lots of mechanisms to help the programmer provide this abstraction. First of all, there's the fact that cancellation is cooperative. So it's possible to ignore the request, and one way to do that is by using some non-cancelable primitive functions that we provide. So if the process is really doing a series of I/O requests that could not be cancelled, let's say it's sending a message to a server and it really can't be cancelled until it gets the response back from the server because it doesn't know what the server is going to be doing in the meantime, then we've got these non-cancelable primitives that are just not going to respond to the requests. And then it's also possible to combine this with parallelism if we're running at a level of the system that supports multiple threads. So, for example, we could push cleanup work into a work pool and have another thread deal with the cleanups so that we can be more responsive and return quickly in the event of cancellation. I've got a couple of final things to say about AC. There's a bit of details here about the implementation, and then I'll give some quick examples about performance on Windows and on Linux. The implementation, as I mentioned, is also available in the source code for the Barrelfish OS, and there's a lot of gory low-level details in that if you want to see how the real all the lowest level parts work. The basic idea, though, is that we start out by running all of the code on a single stack, and we keep track of where we enter a do-finish block on that stack, and we keep track of where we enter an asynchronous block on the stack. So the example here has the stack growing from left to right. We've got some per thread metadata that keeps track of this work queue of pieces of asynchronous work that have been unblocked and are now eligible to run. And we've got a reference to the current finish block structure that's pushed onto the stack when we enter a finish block. Then within each finish block, we have a flag saying whether the block is active at the moment or whether it's been requested to be cancelled. That is, whether we've executed a cancel statement within it. We've got a chain linking the finish blocks together that's used to help implement cancellation. And we've got a count of the number of pieces of blocked work within that finish that we've got to wait to complete until we're able to go past it. So that field there is used for the synchronization at the end of the do finish, letting us wait until we get to the point we can go past the end. This abstraction here in AWI is what we call one of these records of the saved state, either of the point just after the finish block or of a piece of asynchronous work that's waiting midway through. So it's a kind of poor man's one-shot continuation. In practice, it's the stack pointer and the instruction pointer, and a few other saved registers on x86 and x64. So what happens then is we enter a finish block, push one of these records onto the stack, and keep running. So there's not a great deal of work done on entering. And if we block inside the finish, we will update the count to say we've blocked, and we will put the code just after the finish block into this completion AWI slot, so we know where to resume once all of that blocked work is completed. The difficult part is managing multiple asynchronous calls at the same time. And what we do with that is the first asynchronous call we make inside a finish block keeps running on this exact same stack that we're already using. And then if that asynchronous call blocks, then we allocate a fresh stack that we use for the second call. So we're building a form of cactus stack where logically these different stacks form branches of the same thread's execution, splitting out at the points where we start a finish block. So a lot of the complexity in the runtime system is handling the interface between these different stacks and making sure that when we return to execute the function, we're executing it using the right stack pointer on the right piece of stack, and then we deal with the deallocation correctly. So we've got a few statistics here about performance. This first one is very much a micro benchmark. Yeah. So the question is about how this interacts with context switches. And as far as the OS is concerned, all of this is just local to that one process. So at least on Linux and Windows, the process's thread stacks are just areas of memory in the processor's address space. So the fact that we're doing all this wacky stuff doesn't have any effect on switching from one process to another. There are some complexities about interaction with this and OS functions on Windows, particularly about thread local storage, where we have to make sure we pick up the correct pieces of state. So there's a few details like that, but I don't think there's anything we have to deal with especially on context switches. This is some micro benchmark results. Now, we're just looking at the cost of an individual function call, then the cost of calling into an async operation that doesn't block, and the cost of calling into an async operation that does block. Now, the exact numbers in cycles are a bit meaningless when we get to this fine granularity, because a modern superscalar processor will have lots of instructions in flight, and the extent to which we overlap bits of the execution of such a small piece of work with other bits of work in the same function is going to vary depending on the state of the processor at that point in the code. But the main point here is that there's not much of a difference between making a direct function call and making an asynchronous call to a function. And so we're aiming for the same model that exists in the Silk system from MIT, that you should put async in the code wherever it's semantically correct to start work asynchronously. In the same way as with Silk, the model was that you should express parallelism wherever it's semantically correct and rely on the runtime system being efficient in when it decides to exploit that or not. So we have an overhead a couple of cycles when we're calling something that doesn't block. If we do block inside an async, then we've got an overhead of about 1,700 cycles. And the majority of that is the code manipulating the stacks, allocating us a new stack to resume execution on after we've blocked, updating the finish block information so that we know whether we're eligible to go past that or not. Here's a result from that ping-pong test I started out with. The first result is just looking at using a buffer in shared memory and storing a value into that buffer in one thread, and then in another process reading that value out and storing a result back into a different buffer. So we're not really using the Barrelfish message passing abstraction properly. We're just looking at the latency that the particular machine's interconnect introduced here. And I think the cost here was something like a few hundred cycles for data going from one cache to a cache for a different core on a different physical package. So that was fairly typical at the time. I think this was a machine with quad-core AMD processors. If we use the portable event-based interface in Barrelfish, the gory low-level one I mentioned, then the overhead is about 11,000 cycles. So a few hundred cycles in addition above the low-level costs that come from the interconnect. And this really illustrates why we went to such an extent developing that streamlined interface, or really why Andrew Bauman, who did the work in that, how good a job he did on it. Because we're not adding a great deal of cost on top of the fundamental cost we can't avoid from the interconnect. Then if we add the use of AC on one side or on both sides of the ping-pong test, we're again adding 100 or 150 or so cycles to that cost. So although we've got this programming abstraction that is, I think, a substantially higher level, easier to use one than the basic event-based interface, we're achieving something that's not a great deal different from the underlying cost in Barrelfish of portable message passing or the cost that the hardware provided for the communication between those chips. Got a result as well just looking at a very quick experiment with MPI. And so this is an MPI implementation which I believe is using shared memory for communication. So it's reasonably decent. We've not gone into a lot of effort tuning it, so it might be that I'm doing them a disservice and it might be that someone could tune it better. But the point is that it's at least in the same ballpark as a shipping implementation of MPI, while still giving a hopefully nice synchronous message passing abstraction. Got a few results finally from actual programs running using AC. The first one here is taking a piece of the Barrelfish monitor, a system process that is used for managing resources between cores. And that uses a two-phase commit protocol for synchronizing updates to some of these resources. And we've got 3 different implementations of that two-phase commit. The dashed line is a synchronous implementation. And so that's doing a send from a master core to each of the other cores in the machine and then waiting for responses from each of those other cores. Then we've got, in the thinner line at the bottom, we've got the version built over the asynchronous interface, the event-based interface. So there we're writing all of these message handlers directly and keeping track of the state of the two-phase commit as it proceeds. And then the solid larger line is AC. So we've got a substantial improvement over the synchronous implementation. We, as you can see, have a performance hit compared with the event-based interface. But we have an implementation that's substantially simpler. The event-based one here required 19 event handler functions to be written and 5 different types of temporary data structure to be manipulated, keeping track of the state as it's accessed by these different event handlers. So in comparison, the AC function was just one single function, issuing those IOs, using doFinish to synchronize with them all the responses coming back. The next example here is a model of the kind of disk accesses that might be made by a software RAID system. So we're looking here at a machine with 2 Intel SSD devices, and we're running on Windows, and we're looking at the throughput we get depending on the number of I/O operations we expose to those disks. The throughput for the devices themselves should be about 250 megabytes a second. So the peak we'd hope for with 2 of these disks, if we're loading both of them, is 500 megabytes per second. The dashed line, again, is the performance of synchronous operations to each of these disks. So with a pipeline depth 1, meaning that we expose just one operation at a time, the synchronous one has a very slight performance benefit over the asynchronous, but there's not much in it. But then as we expose more operations to the disks, there's, of course, no way to do that through the synchronous interface, but the AC version and the version using Windows Asynchronous IO both perform and scale in a very similar way. We have some similar results again here looking at asynchronous IO across the network. And this is taking a small multi-client server process that's been used as an example with some of the recent work on asynchronous IO in C# and F#. And the result, once more, is that the performance of an AC implementation written in C compared with an implementation using Windows Asynchronous IO, well, the lines are effectively on top of each other here. We've also included the F# and C# implementations just to contrast the difference between programming in native code in C and programming in one of the managed languages. In fact, it turns out a lot of the difference in performance here is not the things you might expect, like the relative performance of the actual compiled code, but it's about the crossings between native and managed code and the management of the data buffers in the CLR in this case. Now, the last example is a simple embedded web server. And here we're looking at a variety of different implementations, varying the number of clients that we have connecting to the server, and looking at, in this case, a synchronous server that just has one thread handling all of these clients using Synchronous IO, versus implementations that use multiple threads to let a program still use the Synchronous IO interfaces while exposing multiple requests to the rest of the OS. So the idea here is just to try to look at whether how we compare with these other alternative ways of using Synchronous IO operations, using them in AC within a single thread versus using them in multiple threads. And the results show that we have a performance loss compared with Synchronous IO when we have a low load, but we're able to scale to better performance than the single-threaded version, and we get comparable performance to the ones that use multiple threads in order to expose multiple I/O requests. So we're not quite as fast as Synchronous IO on the one-thread case, and we're not quite as high performance as having multiple I/O requests if we're in this region here. But as I was saying at the slide with that spectrum of alternatives at the beginning, we're providing something that's providing a good programming model when compared with the synchronous case, and is providing most of the performance benefits that we can get by using multiple threads or by using asynchronous I/O. So I'm pretty much out of time, so let me just wrap up now. The work here is looking at AC, providing composable forms of asynchronous I/O while still programming in a low-level language like C or C++. The UPSLAR paper that I mentioned says a little more about the work. There's some more source code examples. There's also an operational semantics that defines some of these details, particularly when a piece of work is eligible to execute and exactly how cancellation interacts with the message passing primitives that we have on Barrelfish. It also talks a great deal about the integration between the I/O operations and the AC runtime system, and the work that we do managing the stack in order to keep track of multiple pieces of asynchronous work. And as I've mentioned, if you follow the link to the Barrelfish website, that's got the current source repository, and that includes the work here. So I think it's time for a break now. I'm, of course, very happy to take any more questions or talk about this in the break with you. Thank you.